What you're looking at is something called assembly line machinery. In most previous pathways you might have learned, for example, glycolysis, individual enzymes perform each step of the pathway, with intermediates simply diffusing freely over to the next enzyme.
However, in assembly line machinery, each part of the pathway is physically linked together in one large protein complex, where the substrate is bound to a carrier protein to prevent the substrate and intermediates from diffusing away. And it turns out that life has many uses for assembly line machinery. It's used to make fatty acids, a primary energy source in your body, as well as fancy molecules known as polyketides and non-ribosomal peptides.
But instead of just explaining how each of the steps of assembly line machinery works, or making you memorize them, we're instead going to go backwards and reverse engineer step by step how you might have invented your own version of assembly line machinery so that you gain a more intuitive understanding of the process.
Pay attention now.
Fatty acids are an important molecule of life, but how does nature make them? If we look carefully at the structure of a fatty acid, we see that it's mostly a long chain of carbons. So I want to ask you, if you were in charge of figuring out how to make this fatty acid, how might you do it? Think about it. Well, one idea might be, why don't we just get a bunch of carbons and stick them together? Would that work? Well, not quite. As you know, carbons and alkyl groups by themselves aren't very reactive, so these carbons wouldn't just stick together. But it is a good idea to combine smaller carbon molecules together to make a fatty acid change. And this is how life actually does it. We just need more reactive molecules to make this work. Okay, so which molecules are more reactive? What about carbonyl compounds? If you've taken an organic chemistry class, you've learned how reactive carbonyls can be. What if there was a way to use carbonyl chemistry to form long fatty acid chains? So let's say, instead of having the 2 carbon long alkane groups that we had last time, let's replace these with carbonyl molecules. The one shown here is specifically called an ester. Will these react to combine and stick together? Again, not quite. Carbonyls are great electrophiles, but they aren't good nucleophiles. In other words, we don't have anything to actually attack these esters. But if you remember from orgo, ketones and esters actually exist in equilibrium with an isomer, specifically a tautomer called an enol, and these are nucleophilic. Let's have our esters over here in their enolate form, which is just a deprotonated form of an enol. Now, will these molecules be able to react? Well, yes. Let's go through each step. First, the enolate attacks the carbonyl of the ester, creating a tetrahedral intermediate. Then, the electrons can move down to push off the OR group, and boom, we were successfully able to combine the two carbon molecules into one 4-carbon molecule. You'll notice that we actually have to get rid of the C double bond O, and we'll cover later how that actually works. But once that's taken care of, we can repeat these exact steps over and over to make a longer and longer carbon chain. If you remember from organic chemistry, we've actually already learned this mechanism. It's the Claisen condensation, and it's a key reaction to combine molecules to make long carbon chains. However, nature actually uses some tricks to make this process even more efficient. First, to create the ester enolate, nature actually doesn't use the regular tautomerization reaction that you've learned with the deprotonation of the alpha carbon. Instead, what it does is it gets an ester molecule that's 1 carbon longer, and it uses a decarboxylation reaction to form the enolate. Both ways create the same molecule, but nature prefers decarboxylation because the release of CO2 drives the reaction forward. So even though the goal is to add 2 carbon molecules together, nature needs to start with 3 carbon molecules in order to create the 2 carbon enolate in the first place. Secondly, instead of using regular esters with an oxygen, nature actually uses esters with a sulfur called thioesters. And the reason for this is because thioesters are simply more electrophilic due to less resonance stabilization and less orbital overlap. Specifically, for its 2 carbon starting unit, nature uses a particular thioester called acetyl-CoA. And for the 3 carbon molecules that eventually become enolates, nature uses thioesters called malonyl-CoA. Okay, let's put everything we've covered so far together. We start off with a thioester as an electrophile. Again, nature specifically uses acetyl-CoA. Then we need our enolate nucleophile, which we get by decarboxylating malonyl-CoA. This enolate then attacks acetyl-CoA through a Claisen condensation to create a 4-carbon chain. Again, we must remove this carbonyl group somehow, which we'll cover later. But once that's done, we can repeat. Form a thioester enolate through decarboxylation and attack, and do that again and again. And that's how nature makes these long carbon chains. Make sure you understand this logic, because this is the crux of fatty acid synthesis. But as you've learned already in Chem 27, most reactions in nature don't just occur on their own. They're often performed by enzymes, with specific residues and side chains facilitating the reaction process. And it's the same for making fatty acids. There's an enzyme that does these reactions, appropriately named fatty acid synthase. And this enzyme is beautifully intricate, consisting of many parts or domains. First, the ketosynthase domain, often abbreviated as KS, is where the Claisen condensation occurs. The ketosynthase domain carries the first acetyl-CoA group, which is attacked by a thioester enolate. Now, the attacking enolate molecule doesn't just come in by itself. It's specifically carried towards the ketosynthase domain via another domain. Since this domain carries the enolate molecule, it's appropriately called the acyl carrier protein domain, or ACP domain. As a side note, this squiggly line represents a post-translational modification called the phosphopantotheniol arm, or PPAN arm, which is essential to ACP's function. The ACP domain latches on to malonyl-CoA and carries it to the ketosynthase domain, where it decarboxylates to form a nucleophilic ester enolate, which attacks the electrophile on the ketosynthase domain. Notice how the chemistry is virtually exactly the same as what we learned earlier without the enzyme. All we're doing now is associating specific parts of the mechanism to specific domains of the enzyme. There's a problem though, and it's that acetyl-CoA and malonyl-CoA aren't the only thioesters that exist in nature. There's tons more out there. So what's stopping the ACP domain from just attaching to any thioester, and thus creating a molecule that we don't want? Well, our enzyme has another domain whose job is to specifically bind to only malonyl-CoA and acetyl-CoA. It won't bind any other thioesters. That way, the ACP domain can simply pick up the malonyl-CoA or acetyl-CoA from this domain and bring it to the ketosynthase domain without having to worry about whether the thioester is correct or not. The way that this domain selects and binds to acetyl-CoA and malonyl-CoA is called an acyl transfer reaction. So this domain is appropriately called the acyl transferase domain, abbreviated as AT. So to summarize, in the first step, the acyl transferase domain selects the correct thioester, which is acetyl-CoA, which ACP takes and transfers to the ketosynthase domain. The AT domain then selects the next thioester, which is malonyl-CoA, which ACP takes and carries to the ketosynthase domain. At the KS domain, malonyl-CoA decarboxylates to form a thioester enolate, which attacks the acetyl-CoA via a Claisen condensation, forming a longer carbon chain. This molecule leaves temporarily to get rid of this carbonyl group, and is then put back onto the KS domain, and the entire process repeats with another malonyl-CoA so that the carbon chain becomes longer and longer.
So now, we'll finally tackle the problem of what is this magical way to get rid of the carbonyls? Well, a way to remember this is because we are getting rid of oxygens, we are doing the opposite of oxidation, which is reduction. That is, after each Claisen condensation, the ACP domain carries the molecule to another domain, and this domain uses NADPH to reduce the ketone to an alcohol. Because this domain does reduction on the ketone, it's called ketoreductase, or KR for short. You've probably noticed how scientists are a bit uncreative when it comes to naming things. Once the carbonyl is reduced to an alcohol, ACP carries it to another domain, which converts the alcohol to an alkene. Since this domain causes the release of water, it's appropriately called the dehydratase domain, or DH for short. And finally, ACP carries the molecule to yet another domain, which uses another NADPH to reduce this to a single bond chain. Because this domain does the job of reducing, it's called enoyl reductase, or ER for short. These three steps in combination help reduce the carbonyl down to the alkane oxidation level, and are thus called the tailoring domains. And once ACP is done with tailoring, or modification, it carries the molecule back to the keto synthase domain, and the next cycle is ready to begin. The acyltransferase domain selects malonyl-CoA, which ACP carries to the keto synthase domain. Malonyl-CoA decarboxylates to form a nucleophilic thioester enolate, which then attacks the molecule on the keto synthase domain via the Claisen condensation. ACP carries this now longer molecule to be tailored, Kr, then DH, then ER. And it finally brings it back to the keto synthase domain, and repeat. And at the very end, to release the completely fatty acid out into the rest of the cell, there's a final domain called the thioesterase domain that simply attacks and releases the molecule. Now, when you're going through the notes, you'll have to practice each step of this mechanism and understand it well. For example, you'll have to know that the dehydratase domain works via E1CB, which requires very specific stereoelectronic alignment. But hopefully this visual gives you a more intuitive feeling for the bigger picture of what's actually going on. It's kind of beautiful how everything fits together. And that's fatty acid synthesis. The process by which this all occurs, with separate parts being added to a product in a sequential manner, is an example of assembly line machinery. And it turns out that fatty acid synthesis isn't the only assembly line machinery used by nature. For example, nature evolved to realize that if it did the exact same thing as fatty acid synthesis, but it didn't completely get rid of the carbonyl groups, that is, it only did a partial tailoring, then that would result in a diverse set of possible molecules. These are called polyketides, and polyketide synthesis is also done through assembly line machinery. Because the addition of each acetyl-CoA has different types of tailoring, each step requires a separate module or set of domains. What's even cooler is that beyond just the incomplete tailoring, polyketide synthesis is also not just limited to acetyl-CoA and malonyl-CoA. It can use a variety of thioester building blocks, and this can lead to a bunch of different final molecules. Not only that, but instead of simply releasing the molecule at the very end, polyketide synthesis can involve one of the hydroxyl groups on the polyketide chain to attack the initial ester to form a large cycle, a process appropriately called macrocyclization. Additionally, assembly line machinery can even be used to make unusual peptides that aren't normally made in ribosomes, a process appropriately named Non-Ribosomal Peptide Synthesis, or NRPS for short. As you would expect, because we are making peptides, the building blocks aren't going to be thioesters, but instead amino acids. This isn't limited to just the 20 amino acids you have learned about already. There can also be amino acids that aren't used in protein synthesis by the ribosome, called non-proteinogenic amino acids. Like polyketide synthesis, each step of NRPS also requires a separate module. The domains in NRPS, however, are different from FAS and PKS, but they are similar. Like the AT domain in FAS, NRPS uses an adenylation domain, or A domain, to select the first amino acid, though it must use an ATP to activate it first. Then, similar to the ACP domain in FAS, NRPS uses a PCP domain to carry this molecule. The A domain selects the next amino acid using an ATP, and the PCP domain takes it. The amino acids are then joined into a dipeptide. Next comes tailoring. Though similar to PKS, there's not always a tailoring domain. All the proteinogenic amino acids but glycine have an L relative configuration, which means that they have an S absolute configuration, with the exception of cysteine, which is R. When there is a tailoring domain, it can change the configuration of the most recently added amino acid from L to D. In NRPS, this tailoring is done by the epimerization, or E domain. Notice how, unlike FAS and PKS, for which tailoring is done on the previously added carbonyl, NRPS tailoring is done on the currently loaded amino acid on the same module. Then we can repeat. In the next module, the A domain selects the next amino acid using an ATP, the PCP domain takes it, then the C domain causes the molecules to join together. Finally, the thioesterase domain can either catalyze the release of the peptide or, like PKS, do macrocyclization. An important thing to note is that PKS and NRPS can actually be combined. In that way, we can combine thioester building blocks with amino acid building blocks. Just keep in mind that PKS does tailoring on the previous module, while NRPS does tailoring on the same module. PKS tailoring units can act on NRPS added units, but not the other way around.
And that's assembly line machinery. If this picture looked super complicated at the start of the video, I hope you now have a sense of appreciation of how it all works. I think organic chemistry and biology often feel like it's a lot of rote memorization, but I hope this video has given you a better sense of how logical everything is if you look at it one piece at a time. Thanks for watching. If you made it this far, consider subscribing and sharing with your friends. Each video takes me over 100 hours to make, so thank you so much for helping this community grow and fostering a love for biology.